Okay, so just a couple of communications. I sent you an email about April 3rd, which is Friday of next week. One of my graduate students will show you how to use Lagrange's equations to model a two-dimensional hub, spacecraft hub with a two-link arm, a manipulator, just to show you some real-world applications of what we do here. And I'll be here anyways, but that's not part of the things you should expect on your test, but it's, I think, an interesting demonstration of use of the tools that we develop. And I just want to put this on video. I just realized with you that many of the things I put on the calendar on Canvas don't show on your side unless I select EML 5215 and not my name. But all these things that I put on the calendar as reminders correspond to emails I send you. So I always try to remind you. And I'll see if I can edit those things. But I'm only talking about this special lecture, April 6th, we don't have lecture. We have a makeup on the Wednesday after that. So there's nothing on the calendar that you don't know already. But sorry about that. This is my first use of Canvas. And we don't like each other that much, I guess. So what else? I think that's it. We're going to derive Lagrange's equation today. And then after I derive them into two different forms, I'll make a few comments about analytical dynamics in general. So what we've done so far is Newtonian dynamics, which, by the way, is the origin of dynamics. What I'm going to do today is based on Newtonian dynamics. And alternative formulations, Keynes method, Hamiltonian methodologies, anything else that you see after that is based on Newtonian dynamics. The moment you define an inertial reference frame, you are talking about Newton. The moment you use F equal ma, you're talking about Newton. There's no escape. So that's just for those wondering why we bother so much doing classical Newtonian dynamics, because that's the basic thing that you need to do. It's the basis for everything. Everything else is alternatives, and they are usually mathematical constructs on top of Newtonian dynamics. And the constructs that we have defined last time were the following. We said that we defined virtual displacements. This is for a particle. I goes from 1 to 3 partial of r with respect to the qi generalized coordinates, delta qi. So these are virtual displacements. And what would we say about them? They are consistent with what we call the instantaneous constraints. Constraints. Now, this instantaneous means no passage of time. So you're freezing time, and you let the particle, in this case is 1, then we'll do for system of particles. But in this case, you let the particle move as it is allowed to move given the instantaneous constraint, whatever is your constraint at that particular time that you're freezing. So you don't let time go by, you freeze it, and you just look at what can happen. So we saw last time, if you have this pendulum here where the attachment can move with a certain law of time, this is O, this is your angle theta, and this is your mass down here. The instantaneous constraint is whatever is the position of O right now. And the only thing that this particle can do is move in a circle around that point. And in this case, I only have one q, which is theta. So the dr d theta is giving me the direction in which I can move, which is consistent with the constraint that is frozen in time. So is this concept of virtual displacement clear? There is nothing fancy about this. This is a clear definition. This is what a particle in this case, and will extend to probably system of particles and rigid body, but this is what a particle can do when I freeze the constraints. Constraints can move around. This attachment point, I can put it in a circle and make it move around. I can just move it in space. But I remove that option, and I focus on what the particle can do with the constraint that is fixed. Okay? Questions on this? No questions. Okay, that's what we defined. And then we said that if we sit on the particle, with the particle, let me call this the resultant of all forces acting on the particle R. It will be clear in a second why. We said that we don't see any forces or accelerations on that particle because we are attached to it, so we have D'Alembert's principle. And these are the two things that we're going to use to derive Lagrange's equations. So I'm writing the forces as R because I want to split them into F plus C, where this C is the constraint forces. And I can really just say force because I'm talking about one particle here. So that's the action that comes from the constraint. That's what's keeping, in the example of the pendulum, it's the N acting on the particle that it's keeping it moving around point O, right? It's what keeps you on track. So if you are on a roller coaster, for example, you're doing something like this. This is your particle P here of mass M. So this C is what keeps you on the track. And at that time, maybe pointing somewhere else. I don't care. This is just a representation. I'm not talking about friction here. So anything else goes into F. C is only that force that keeps you on the track, which, as you can imagine, is perpendicular to the virtual displacement. Right? So if this is your constraint, this is your guide. You're moving on this guide. This guide can move in time. It could do something else other than just stay there, fixed in an inertial reference frame. But when I talk about virtual displacements, it is not moving. I'm freezing the constraint. And so this is dr, d, whatever is your variable. Say that you only have one, dq1. So, you know, and so the dot product between these two needs to be 0 if I'm looking at the instantaneous constraint, right? So I can actually write C dotted with dr needs to be 0. I'm not sure where I'm putting this dr, dq. Let's just call it dr. This is dr, I'm sorry. Yep. Okay, does it make sense? And so with that in mind, if I take this expression and I rewrite it like this, F plus C minus M A N, and I dot it with a virtual displacement, again, this is something that occurs without the passage of time, is the motion of your particle, which is consistent with whatever is the constraint at that time. If the constraint changes another time, I don't care. So this needs to be what? This is 0, right? This was 0, so one of the two vectors here in this dot product is 0, so it doesn't matter what I do. When I dot it with something else, it will be 0. But in particular, I am constructing my theory here saying that this particular dot product is 0. And this is what is called virtual work, as you can imagine. It's a dot product between a force and displacement, which is a virtual one, so let's call it a virtual work, as the dimension of work. So the instantaneous constraints don't make virtual work, any virtual work. They can make real work. So if the particle is moving on this track, the velocity will be tangent to this delta r, in the instantaneous case. But if then this track is moving, then the real velocity in the inertial reference frame is not necessarily tangent to that line, if the line is also moving, right? So that dot product, so your actual velocity in an inertial reference frame could be something like this, v in n, if this whole track is moving. So this is not true in general. The constraints may make work, but they don't make any virtual work. That's why I'm freezing time, because it allows me to say that, which I'm going to use. Questions? No questions? You look like you don't know what's going on. Is there anything confusing about this? This is just defining ingredients to find Lagrange's equations. There's nothing else here. Not really demonstrating anything. I'm creating the pieces that I will need. I'm free to decide that constraints don't evolve with time, and I define this virtual displacement. This is of course true, and I'm observing if the constraints are frozen, they don't make any virtual work, which should make sense. Okay, so let's use these things. Since I'm talking about work, what does work do? When you have forces that have non-zero work in general, remember this is for the constraints, but then there are other forces here that can make also virtual work. What does work do in general on a system? What does it affect? This table is at rest. If I push it and it starts moving, what am I changing on the table? Its velocity, so kinetic energy is changing, right? So that's where we start for derivation of Lagrange's equation. We start from the definition of kinetic energy, which is extremely simple for a single particle, of course. And we'll start taking some derivatives, and then at some point use these two things here that we have. No virtual work for constrained forces. And this is what will lead to finding equations where you don't care about the constrained forces and those reactions anymore. That's one of the beauties of Lagrange's equations, that you completely forget about the constraints, because I derive the equations including this fact in them. So very powerful. Unless you want to know what those forces are, but if you don't want to know them, you just forget about them in the Lagrange's formulation. Okay, so kinetic energy. Let's start from there. T for a single particle is 1 over 2 m. Okay, I told you last time that for Lagrange's equations, we do work in an inertial reference frame. So I'm going to drop the n, where n is an inertial reference frame from now on. But everything, please remember, it's in an inertial reference frame. So this v, if I say v or I say a, v is d dt in n of your position. I'm not going to work in other reference frames, even though in solving problems with Lagrange's equations, there's no escape. You may need to compute this velocity using the transport theorem, so you need to be careful with your different reference frames. There's no escape from that. But what I'll derive is only valid for the inertial reference frame. So, and I start from the kinetic energy in an inertial reference frame. So I'm going to play with this to get to my final result, and I take the partial of t, for example, with respect to qi, just for fun. This gives me mv dotted with dv partial of v with respect to qi. One thing we want to remember here is that I have parameterized my position with, at the most, 3 generalized coordinates. This is something that we've seen last time, right? We're doing a particle here, so can't have more than 3. Okay? So if r is a function of those coordinates, v will be a function of those, and I don't know what it is, because I'm doing it in general. We'll specialize it for every single problem, but this is always valid, right? And is this clear, what I'm doing here? Is the partial of this times this plus dot with this plus v, the partial, and you can swap them, so the 2 goes away. We've done it before. dt in dqi dot is the same kind of expression. The only difference is that I have dv in dqi dot. And then let me compute that. dv in dqi dot. Okay. Well, if r is given as a function of 3 scalar quantities, coordinates, and by the way, these are independent from each other, of course. You would never pick x, y, z coordinates with x equal to z. Those are not valid coordinates. You have a relationship between two of them, so they're not independent. They're not legit coordinates. Go back to your 3, 2, 1 ordered angles. Second rotation is 90 degrees. The first and last rotation occur about the same axis. That's not a valid set of coordinates anymore for that particular configuration. So they are coordinates, so they need to be independent from each other. So if R is expressed like this, then V, what is V? We said this last time, that V would be basically the summation over I, that goes from 1 to 3, of the partial of R with respect to Qi dot, right, plus the partial of R with respect to time, if that's the dependencies that I have. And so dV, partial of V, the velocity, with respect to Qi dot, is equal to what? You sure about the summation? This is one of the i's. I goes from 1 to 3. I'm only doing partial of V with respect to Q1. So it's only dr dq1. Okay, so this is dr dqi. So put these two together gives me that the partial of V, sorry, of T, kinetic energy with respect to Qi dot can also be expressed as mv dotted with dr dqi. Okay, nice. Okay, so can probably use this down here for a while. I'm going to start taking derivatives with respect to time because that's what we do. And again, I'm not going to write this n, but that's assume that it's there. I'll start taking the derivative with respect to time of this partial here. dt partial of t with respect to qi dot. What is that equal to? This is what I am derivating with respect to time. Well, it's m is a constant, so it will be the partial of v, the derivative of v with respect to time dotted with this, plus v dotted with the derivative of this with respect to time. So I have m a, and again I'm dropping the n, but this is acceleration in the inertial reference frame, dotted with dr dqi, plus mv dotted with d dt dr partial of r with respect to qi. Agree? Now this can also be expressed as what is ma? R plus c, right? And see, this is the step where I'm using what? Newton's second law. So what I'm doing here is a bunch of mathematical calculations, taking partials and time derivatives, having defined the virtual displacement, D'Alembert's principle. But guess what? To move on, I'm going to use Newton's law. So don't let anyone tell you that this is something that you can use whenever I get to the end. These are formulas you can use instead of Newton's laws. It's an alternative way of solving dynamics that may be convenient for some problems. But you never throw away Newton's Newtonian formulation. That's the basis for everything. Without that, there will be no Lagrange equations, no Keynes method, no anything else. Because every time you say that there is, even before this step, I use the definition of inertial reference frame. That didn't come with Lagrange, that was before Lagrange. So just making sure that we understand what it is that we're doing. This is just a formulation that happens to have advantages, but it's not telling you you can use this and forget about Newtonian mechanics all at once. You cannot do that. So r plus c dotted with dr dqi. Now this is I can change the order in which I take the partials here, because q and t are really independent. They better be independent. Those are coordinates. They cannot depend on time. Can you imagine defining, I go always back to the Cartesian example. Can you imagine defining x, y, z that they depend on time? Why would you change, once you set a coordinate system, why would you keep changing it? That would be crazy, right? So I can swap the order there, and that gives me mv dotted with ddt of r is v. So that's the partial of v with respect to qi. Do we agree with this step? This partial of v with respect to qi is something that, what am I doing here? That I have somewhere. Oh, no, the whole thing, yes. mv dv dqi is dt dqi. So let me go down here. I add d dt of the partial of the kinetic energy with respect to qi dot is going to be, let me bring these on the left-hand side, so that becomes minus partial of t with respect to qi. We're almost there. Equal to this term here. That's r plus c dr dqi. This is a dot product here. OK. So what I'm going to do now is, I'm going to do whatever I want with this, manipulate it even further. I'm going to actually multiply the whole equality times a virtual change in one of the q generalized coordinates, and then sum over all of them. So in other words, what I'm going to do, I'm going to bring this on the other side, becomes a minus. Multiply the whole thing times delta qi. This is going to be 0, of course. Summation over I. OK? Move back here. Why am I bothering doing all this? Just for one reason, that I want to exploit the fact that C is not going to make any virtual work. Because in that summation, if I only focus on this term here, summation over I of R plus C, and note that these two don't depend on the I. I have dr dqi in partial of R with respect to qi delta qi. And so this summation can go here, because R and C don't really depend on the I. And so summation of partial of R with respect to qi delta qi is what I defined before as the virtual displacement, right? Is how you can move, is your change in position, which is consistent with the instantaneous constraints. So this dot product here that I have with C goes to 0. So the bottom line is that all I have left is this R dotted with summation 1 to 3 partial of R with respect to qi delta qi. Agree with this?
That will be if, right? It will be if plus C into dot R plus C.
Yes. What is it? I'm sorry.
It will be if plus C, right? R is a summation. R is a.
Oh, I'm sorry. This is F. Yeah, I called it F. Thank you. I have it everywhere as R. See, that's. I decided to switch the letters, and I'm still sticking with something else that I had in mind. OK. Anywhere else? Thank you. Yeah, R is yeah. So basically what is left here is summation of all forces acting on the particle except the ones from the constraint. The ones that are perpendicular to the constraint, that keep you on the track. OK, so basically if I put it back in there, this is what I get. Summation I 1 to 3 d dt of partial of the kinetic energy qi dot minus partial of the kinetic energy with qi. And then what else do I have? I have plus f dotted with minus, I'm sorry, this is a minus f dotted with partial of r with respect to qi. And then this is multiplying some virtual change in the variable qi. Looks okay? Now, these QIs are independent. All these delta QIs, they all go by themselves in different directions. They have no relationship. So to have this thing to be 0, every single one of these for any I needs to be 0. Imagine what is going on. This is a summation of 3 components. Whatever this is for Q equal 1 times delta Q1, whatever this is for Q equal 2 times delta Q2, plus whatever this is for Q equal 3 plus delta Q3, that needs to be 0 for any generic combination of delta Q1, delta Q2, and delta Q3, which are independent. So the only way is that what is multiplying the deltas are all zeros. And that's my final result. I can write that I have the almost final result, d dt of the partial of the kinetic energy with respect to qi dot minus dt qi, partial with respect to qi, is equal to f dotted with the partial of r with respect to qi. That's it. This is, I think your book calls this as the, I think it's called the fundamental form of Lagrange's equations. So in other words, and we'll try to do an example maybe today, I don't know. If you have a system that has constraints and it's convenient to use this formulation because you pick some variables q's, that can be anything. They can be x, y, z, but they can also be an angle and an x, a length and an angle. You can do whatever you want. It may be convenient to write your kinetic energy, take its partial with respect to these variables that you picked, the partial with respect to the derivatives of those variables, and implement this expression, which is not a formula. This is Newton's law projected on 3, in this case 3. In general, you will have more than 3 if it's a system of particles, in a certain number over a certain number of non-orthonormal generic directions. So everything we've done in Newtonian dynamics was using most of the time, except with other angles, orthonormal basis. These q's can be anything now. So you're projecting your Newton's law, and again, there is Newton's law because I did this. I went from this to this. So I am using Newton's second law. This is a projection of that in a certain number of generic directions that you may have picked to choose for your problem. You may happen to choose for your problem. So this is not a formula. This is an alternative. What we call here, this term here, f delta partial of r with respect to qi, it's usually called q, capital Qi, and it's called the generalized forces. By the way, let me add, since we are still dealing with a particle, this is for I that goes from 1 to 3 at the most. It could be less than 3. In the problem of the pendulum, that I is 1. I only have one variable, which is the angle theta. And note that those generalized coordinates, generalized forces, they don't need to be forces. That's why they're called generalized forces. They can have dimensions of anything. It can be the dimension of a moment. It can be the dimension of something else. So they're not forces. It depends on what it is that you picked as your variables here. Okay? One more thing that is done usually is the following. That Qi, if you can, is not always the case, could be in some problem split as Qi prime minus the partial of a certain function v, and I know that I'm using v for velocity and a function here, but this is no underscore, so it's just a function with respect to Qi, where this v is called potential function, is not a potential energy. It could be, but it doesn't have to be. It could be in some cases that it's actually an energy, but you may have certain forces or generalized forces that you can express like that, where you can define a scalar function such that its partial with respect to Qi gives you the corresponding Q. So this would be all the other forces that cannot be expressed like this. One good example that we'll probably see is springs. You can write a potential energy for a spring as long as the attachment point is fixed in an inertial reference frame. So you can write a U for a spring. But if the spring has the two ends that are free to move in the inertial reference frame, two masses are attached at the end of the spring, at the ends of the spring, you cannot write the potential energy. It's not a conservative force anymore, but you can still write the potential function. You can still write something like this that allows you to split the generalized forces in two components. And so if we have some cases where this is possible, again, we'll see examples, we define what is called the Lagrangian function, which is T minus V. Lagrangian function. And you note that the partial of this function with respect to q dots is 0. It doesn't depend on the q dots. And so another formulation, which I think is called, let me grab a longer one here, in your book is called the standard form of Lagrange's equations, is the following. You have d dt of the partial of L with respect to qi dot minus partial of L with respect to qi equals this qi prime. So these are all the generalized forces that I cannot express as the partial of a potential function. So this is, again, for I that goes from 1 to 3, and this is the standard form. Again, the beauty of this formulation is you can have your coordinates now to be anything, a mix of angles and lengths and et cetera, et cetera. It doesn't matter, you're projecting Newton's law in non-orthonormal directions, and please note, there is no more constraints. That F has nothing to do with constraints. Those are all the forces except the constraints ones. The constraints ones are gone because they make no virtual work, and I got rid of them to get to these two results. Can you find the constraint forces if you use Lagrange's equations? No, you will have to go back to Newtonian mechanics and back them up from there if you really need them. But if you don't care what they are, you want to find your equations of motion, that annoying part of eliminating the reactions is gone here. So those are the two beauties of this formulation. This is an alternative to Newtonian mechanics. It's not a substitute. It can be a substitute because you solve problems like this, but it comes from there. Without Newton's law, I couldn't even write these equations. So let me go back to the pendulum. Any questions? Don't ever tell me that these are formulas. These are projections of Newton's law. If you write that on a test, that's bad. I'll write the Lagrange formula. Nope, don't want to see that. The same way as F equal ma is not a formula. It's a law. This is a projection of that law. Okay, we had this pendulum example that we started from talking about virtual displacements, etc. And let me do the case where the attachment is not moving. We had a massless rod here that leads to a mass m. The angle that we pick as our coordinate, so I only have one, is theta. And of course there is gravity, otherwise there would be no pendulum. Attachment point is O, and this is inertially fixed. And I want to write the equations of motion with this formulation. Note that, again, you can't forget at this point anything that we've done so far. If that attachment point was moving, in the first step for finding the Lagrange's equation, which is writing the kinetic energy, again, I drop the n, but it's there. This is the velocity in the inertial reference frame. So if this point O was going to move, then you will have to take that into account. You have to do your kinematics anyways. There's no escape from that. So, but in this case, the attachment point is not moving, so this is easier to find. Okay, so we start from that. We write that the velocity is what? R equals L. And now I'm skipping the steps just because I want to try to finish this. But of course, there is an inertial reference frame, which is the ground. Let me call it N or G, whatever. And we define the other reference frame that is always attached to this arm. And then we have the coordinate system attached to it, which is little er here, little e theta here, right? So I'm assuming that you will go through doing this in a problem, but I just want to use those equations now. I call them equations, by the way. They are equations. They're not formulas. OK, so what is the velocity? Can you tell me? L theta dot E theta. So this dot product here is 1 over 2 mass L square theta dot square. Fine. What is the partial of this with respect to, let's start from this one, from respect to Q, again, Q1 is only one, it's theta. What is this? 0. We like zeros. And then the partial of t with respect to theta dot is m L squared theta dot. And then I need to take the derivative of this with respect to time. Okay, d dt of partial of t with respect to theta dot is ml squared theta double dot. Okay, that takes care of the first, the left-hand side. Now forces, free body diagram. There is also no escape from this. You have to figure out the forces. There is mg, gravity, and there is n, whatever is keeping me on track on that circle around O. Do I care about n? That's a reaction force. I don't care about n in Lagrange's formulation. So the only thing that I need to compute in my Q theta, because I only have theta here, is what? Is mg dotted with the partial of r with respect to theta. I think we did this already. What is this? mg. What is the partial of r with respect to theta? L is constant, so it will be the partial of how ER changes as you change theta, and we said that that's a unit vector, so that change will be perpendicular to it, and it happens to be this. And if you're not convinced about it, you can demonstrate that yourself once you go home. So what is this dot product here? MGL. What is the, I'm calling, I don't know, call this EY, the vertical direction pointing down. So what I'm left with there is I need to figure out what is EY dotted with E theta. What is that? If I was doing it with this guy here, ER would be a cosine of theta. This is probably a minus sine of theta, right? Minus sine of theta. I'm done. I'll put it all together. Yeah, I don't need this anymore. The only Lagrange's equation that I get, which again, it's a projection of dynamics, so that's why I get equations depending on how many coordinates I have, is this term, ml squared theta dot equals minus m. That's your equation of motion. Well, you can simplify things, of course. I'll do it here. Okay. Now, since there is a little bit of time, what about we do it with the alternative or standard formulation where you have d dt of partial of L with respect to qi dot minus partial of L with respect to qi equals whatever I cannot write as a potential function. So in this case, is there anything that I cannot write as a potential function in the in terms of the forces acting on that particle? Remember, constraints forces are gone. We don't care about those here. The only thing I see is mg's gravity. That is actually a conservative force because it's a constant force, and I'm assuming that all of you have read the chapter about conservative forces and the potential energy. So I can write not only a potential function for that, it's actually a potential energy. So what is that potential energy for gravity? I don't want to start. And these are the things you don't need to memorize. You can look it up in the book. Anyone remembers? No? No one? Are you doing problems? Does it look familiar? No? That's what it should be. Okay, so I don't want to erase stuff that I should keep. I should have kept the kinetic energy. What is the kinetic energy? We said that before. That was 1/2 mass L squared theta dot squared. So my L will have to be this plus mg dotted with r. See if I get to the same equation. I should. Okay, what is this? Except is 1/2 m L squared theta dot. Okay, now I'm doing the dot product between, well, mg is, no, g is some g ey, and r, I just erased it, is L er. Now there should be a cosine of theta here, right? So that's mgl cosine of theta with a plus. Sounds reasonable? Okay. Now if I start taking the, I'm looking at this formulation down there. If I start taking the partials, well, the first one, the partial of L with respect to theta dot is the same. We said that this potential was not going to depend on the dots of the Q's, and that's in fact what I have. So it's the same as before. It's mL squared theta double dot. Then the partial of L with respect to theta. I'm not doing the derivative with respect to time for now. Oh, I'm sorry. Yeah, there's no double dot, of course. And so dl d theta, this is L. There is no theta here. There is a theta here. Is a m minus mg L sine of theta. Okay. The ddt of these is, of course, what I had before, mL squared theta double dot. The q, we said that q, well, I only have theta here. Q theta prime is 0. So when I put it all together, I should get the same thing. mL squared theta double dot minus the partial of L with respect to theta. So minus is plus. So I'm just bringing it on this side. And of course, I get the same thing. And that's equal to 0. So you can see it's the same equation. Now, do you need to do it at any cost in this way when you have conservative forces or just forces that can be expressed as a potential function, not necessarily a potential energy? No, you don't have to. If you don't have your book and you're desperate that you cannot figure out what the potential function is, who cares? Just do it this way. This is the general way. All the forces are in here, conservative, non-conservative, whatever that is, except the constraints. The only things you can throw away are the constraints. Anything else can go in here and use the fundamental form, and you're done. Any questions? This is a very simple problem, but I'm just showing you how it is an alternative to Newton's approach, where I don't care about the constraints. And since we have 5 more minutes, I think I want to just start telling you what this becomes when you have a system of particles. I'm not going to demonstrate anything in particular. But if you have, what are we going to call them now? Say that you have, let's have n particles. I will reformulate these a little better next time. And let Q1, let's call these, we say that these are m particles so that the coordinates are n. So let Q1, Qn be generalized coordinates. Representing the configuration of the system so the system is those m particles, of course. Well, Lagrange's equations, again, I'll go over this again. They will pretty much look the same. The difference is that now the kinetic energy, so I'm looking at this formulation here, is the kinetic energy of the system. So you have to add all the kinetic energies together. So T will be the summation of all the T I, where I goes from 1 to m. So you need to add them all together. And you will get the same kind of expression, except, again, this is now qi dot minus dt dqi. The difference is on this side here. This qi, it's now a summation, because you have a bunch of particles, and each one of them has a resultant force, except the constraints forces, that is acting on each one of them. So the r's are the positions of all the particles. So I need to add here on the particles. So I goes from 1 to m. What? The fi. Oh, I'm sorry, I'm using the same index. No, let's call this j. Makes it better. So fj dotted with the r partial of r j with respect to qi. For I that goes from 1 to n. So for a system of particles, pretty much is the same. You need to be careful that you add all the kinetic energies together, and that's what you're using here, the total kinetic energy of the system of particles. And then for each, so you have one equation for each coordinate. For each generalized coordinate, you get one Lagrange equation. And so for equation number 1, I is 1, I is 1, I is 1. Well, here you have a summation. You have to go over all the particles, know what are all the forces on each particle, its position, take its partial with respect to that to the variable you're looking at right now. And so this will be a little longer, but it will be pretty much the same thing. And the problem that I'm going to do next time, I'll restate all this because this was kind of quick, is something kindly suggested by one of your colleagues. So it's a simple problem, but it's a very good one to show how you can use this. 3 springs, different case, 2 masses here. This is, of course, the ground. This is fixed to the ground. This is fixed to the ground. So we'll find the equations of motion of these using their formulation. Maybe we'll also do it without the standard form, writing a potential function. So this spring will have a potential function. It doesn't have a potential energy because none of the attachment points is fixed in the inertial reference frame. So this will be a good refresher actually here. We'll refresh the force of a spring and a few other things. And so we'll solve it with the classical Newtonian approach and then with this approach. And you will see, again, I'm telling you at this point, how you cannot forget anything that we've done, because it will all come back at some point. There's no, this is a continuous learning process. You can't skip any steps. Try to solve it yourself, I guess, before we meet next time. Okay? Thanks.